Good afternoon, Calc 3 gang. I wanted to continue our final chapter in Calculus 3. In fact, all of your study of calculus here at C of O. That's pretty exciting, isn't it? I forgot to point that out. This is the final chapter. So buckle down and hang in there with me, and let's get through this content. It's really quite interesting and quite fun. So I'm excited about it and looking forward to working through it with you. So last time we learned about line integrals, lots and lots and lots of line integrals. We had line integrals of scalar functions, and you could do scalar functions with respect to arc length or with respect to x or y or z if you have a z. And then we learned how to do line integrals of vector fields as well, and we learned how to interpret those. They represent work done by the vector field moving a particle along C. And we saw last time the connection between line integrals with respect to x, y, and z and line integrals of vector fields. And so today I want to look at what's known as the fundamental theorem of line integrals with you. And I'll often shorthand that as FTLI. So before we do the fundamental theorem of line integrals, I thought we should review the fundamental theorem of calculus. And you're going to see the basic ideas behind the fundamental theorem of calculus show up again and again and again in this chapter. It's really quite beautiful. So the fundamental theorem of calculus, the part that I want, says that if you have a definite integral from a to b and you're integrating f prime of x dx, then this is nothing other than f of b minus f of a. And, you know, it's difficult for us to appreciate this fully unless you've actually computed a bunch of integrals by the definition of the Riemann sum, which we typically don't do very many of those. I think I did maybe one or two of them with you just to show you how it works. But we typically use this to evaluate integrals. But this is a really big result, and it makes computing all kinds of areas possible. We've used this in Calc 3 to get certain double and triple integrals. Right? They boil down to being able to do this. So a huge result, and you're going to see a very similar result for line integrals. So here we go. So here's the setup. This is the fundamental theorem of line integrals. So I want a smooth curve, and smooth just means that there's no cusps. It doesn't have a cusp like that on it. Smooth curve given by a vector function r of t, a from t to b, and I'm going to let f be a differentiable function of 2 or 3 variables, I don't really care how many, whose gradient, the gradient of this f, is continuous on C. And what that means is each component function of the gradient is continuous on C. So then in that case, it turns out that the line integral over C of the gradient of f dot dr, now let's keep in mind, this is a vector field. So this is really just the line integral of a vector field dot dr. It turns out that it's equal to f of r of b minus f of r of a. It's very, very similar. Before, it was f of b minus f of a. Here, you have this interval. Your t's are between a and b. The curve itself, right, is actually starting and ending at certain points in space. And so you plug in the end point. Let's say we're going this way. You plug in the end point, that's your r of b, and then you plug in the beginning point into f, that's your r of a. So really nice results. It's going to make simplifying certain kinds of line integrals much easier for us. Let's actually write down what I just said. Maybe I'll switch to green here. This is the end point, and this is the starting point. I want to make sure that's clear. Okay, so a couple of morals. Math does have morals, believe it or not. So you can use the potential function of a conservative vector field to evaluate line integrals of conservative vector field. I just said that. So this is very useful for conservative vector fields. Doesn't work if you're not conservative, because if you're not conservative, you're not the gradient of something. And then one other comment, line integrals of conservative vector fields are actually what's called path independent. And let me show you what I mean. So suppose that we have 2 points, and this point, I'm going to think about this point as being r of a, and this point is r of b. And now I'm going to give you a bunch of different parameterizations. So one way you could get from the first point to the other point is like that. Another way is to go around like this. let's do something crazy. Let's go, around and then back and then forth and then back and then forth. And I hope you get the point. I could just keep drawing these all day. Maybe I will because it's so much fun. But it doesn't matter what curve you pick, because any of these C's with all their different parameterizations, at the end of the day, if you're evaluating a conservative vector field f, if big F is the gradient of a little f, then this is just f of r of b minus f of r of a. You just plug in the endpoint, and then you subtract, plug in the beginning point. So it doesn't matter what path you pick. You can switch paths, and it doesn't change anything. So we'll look at this more as we go along. I think in the next video we'll dive in and work out an example.